In this video lesson, we're going to cover probably one of the most important and classical examples when it comes to energy, and that is the roller coaster. Before you attempt this video, I want to make sure that you've already gone through and you've done the notes on how to quantify or calculate three different types of energy. Elastic energy, but more specifically and importantly, kinetic energy and gravitational potential energy. If you look at the animation that's on the screen in front of you, you'll see a very simple example of a roller coaster. As the cart goes through the roller coaster track, I want you to notice some things that are changing. One, right below, you can see the height and the speed is given. But more importantly, I want you to notice on the side, there are three columns. KE stands for kinetic energy, PE stands for potential energy, specifically gravitational potential energy, and then TME stands for total mechanical energy. And I'll write that out. Now, what's really important to notice is that as the cart is going through the roller coaster track, the total mechanical energy represented in green never changes. That's because the total mechanical energy represents the total energy that is used in the system. In other words, it's the energy that is used to make the object do something. As the cart is going through the roller coaster track, the total mechanical energy is conserved. This is known as the law of conservation of energy. In other words, energy is not created or destroyed, but instead it is only transferred from one type to another. And that's what the first two columns are doing. If you'll notice, as the cart is going through the track, the energies are changing types, from kinetic to potential, but they're always adding up to be the third column, which is in green. Now notice at the beginning, all is potential. As the cart moves down, it turns into kinetic. Its highest kinetic is at the bottom, and as the cart gains elevation or height, it transfers back into potential. This is going to be very important for the problem that we do right now. So let's go ahead and look at an example with some numbers. On the screen in front of you, you'll see something that is very similar to what we just saw on the previous slide. What we're going to do is we're going to look at a cart that has a mass of 50 kilograms starting up here at position 1. The cart starts at a height that's 4 meters above the ground. As the cart moves down the ramp, it'll go through a loop that is 3 meters high, go back out of the loop, and then go over a hill. There are going to be 4 parts that we will analyze in this problem. Before we do this problem, I'd like to show you an animation that shows you this exact situation. What I'm going to do is I'm going to play this. As the cart gets to the top, it's all potential. Then it goes down, and you'll notice how the energy is changing as it goes through that motion. Let's play it again. As elevation changes, it turns all into potential. At the bottom, it's all kinetic, and then it gains a mix as it goes through. The pie chart that you are seeing at the very top is one way to show how the energy is being stored. All potential, all kinetic, and then as it changes and goes through. Now there is another way that we can show how energy is being stored, and that is what we're going to do at the bottom of the screen, which is through bar charts. What we're going to do is we are going to chart the energy using bar graphs for each of those 4 scenarios. So let's go ahead and do that. Excuse me. Okay, so we've got 4 spots that we are going to analyze. Spot 1, 2, 3, and 4. As we go through each spot, let's think about the energy that is going to be there. At spot number 1, the cart is at its very highest point. Since this is where the cart starts, all of the energy is Eg. It's not moving yet, so there's no kinetic energy. Kinetic energy will come as it goes down the ramp. Since the cart is not attached to any sort of spring, there is no elastic energy here. And so all the energy at spot 1 is going to be gravitational. So what I'm going to do is I'm going to create a bar chart with all the energy being stored as gravitational energy. This represents the total mechanical energy that is in the system. These bar charts right now are going to be qualitative. We're not going to put any numbers in yet because we haven't done any calculating. But what I would like you to notice is how many squares represent the Eg. If you count up vertically, there are 7 squares. What we need to make sure is that we always conserve 7 squares of energy as we go through this problem. Okay, so let's go ahead and look at spot number 2. At spot number 2, the cart is now upside down in the loop. So we ask ourselves, what energy is here? Well, it has Eg because it is in the air, but the cart will also be moving at this point, so it'll also have Ek. Now at this point, it's qualitative, but it's also good to make sure that we can represent the energies relative to one another with the appropriate size. At spot 2, which energy do you think is higher, Eg or Ek? I would predict Eg is higher, because at spot 2, the cart is 3 meters above the ground. If you compare that to the original height, which was 4 meters, that's not much of a difference. The cart is almost back up to its original height. Since it's almost back up to its original height, you'd imagine Eg would be highest at that point. So what I'm going to do is I'm going to maybe put 5 squares of Eg and 2 squares of Ek. Once again, it's all qualitative right now, but I want to make sure that my vertical number of squares is equal to 7, because I want to show that the total mechanical energy is conserved. All right, let's go ahead and look at spot 3. At spot 3, the cart is now at the bottom level. It's at my reference level. And so at that point, there is no Eg. It's going to be all Ek. And so at spot 3, I'm going to show all 7 squares as Ek. Finally, at spot 4, we see that the cart is on a hill, so it will have Eg because its elevation has changed. And it's also moving, so it'll have Ek again. Now, at this point, we don't know the height, we only know the velocity. For right now, we know there's going to be a mix of Eg and Ek, but how much is greater we don't know for sure until we calculate. Let's go and make a hypothesis. Let's predict that our Ek will be higher than our Eg. So I'm going to go ahead and maybe make Eg 3 squares, and I'm going to make my Ek 4 squares. Once again, I want to make sure it all equals 7 because energy is conserved. So now what we have done is we have made our bar charts that represent the energy as it goes through all 4 stages in the roller coaster. Now what we're going to do is we're actually going to calculate the energies in each of those spots and use that energy to calculate some quantities. All right. The first thing I would like to know is what is the total mechanical energy in the system? In other words, how much energy is there always going to be total? I can technically use any bar chart to do that, but I need to make sure I have enough information to do that. For example, I could use bar chart number 3 to calculate what my total mechanical energy is. At spot 3, the total mechanical energy is all kinetic. If you remember, the equation for kinetic energy is 1/2 mv squared. So if I could calculate the kinetic energy, that would tell me my total mechanical energy, since it's all Ek at that point. To do that, I need to know 2 quantities, the mass and the velocity. I know the mass is 50 kilograms, and that's constant throughout the entire coaster ride. But I do not know what the velocity is at spot 3. So I actually cannot use bar chart number 3 to help me figure out what the total mechanical energy is. But no worries, we have 3 other bar charts we can use, because remember, the energy is going to be the same in all 4. Since I like the idea of only having to deal with one energy at a time, let's see if we can figure it out from bar chart number 1. Bar chart number 1 has all of its energy stored as gravitational. And so if you remember that equation, gravitational is mgh. In order to figure out the total mechanical energy, I would need to know the mass, which is 50 kilograms. I would have to know what g is, which is the acceleration of gravity, which is 10 meters per second squared. And I would have to know the height, which I do know, it's 4 meters. So 50 times 10 is 500, times 4 is 2,000 joules. So not only do I know that the gravitational energy in the first bar chart is 2,000 joules, but I also know this is going to be the total energy for every bar chart. The energy in bar chart number 2, bar chart number 3, and bar chart number 4 all have to total to be 2,000 joules, since the energy is conserved. Now you'll notice in none of these bar charts there's no dissipated energy, meaning this is a frictionless roller coaster. So the only energies we have to concern ourselves with is EG and EK. We've already done spot number 1. Let's go ahead and move on to spot number 2. You'll notice spot number 2 has a mixture of both EG and EK. To figure out EK, I have to know the velocity, which I don't know at spot number 2. However, I do know the height at spot number 2 is 3 meters. And so I'm going to use my same formula as I used before to figure out my EG. My mass is still 50, and gravity's acceleration is still 10, but the height now is 3 meters. And so 50 times 10 is 500, times 3 gives me my EG as 1,500 joules. Since energy is conserved, I know another 500 joules must be what EK is. Looking at number 3, you may notice that we still do not know what the velocity is. But remember, energy is conserved. Since all the energy has been converted to kinetic at spot number 3, we know that the kinetic energy at that point must be 2,000 joules. Finally, at spot 4, we have a mixture again, EG and EK. However, this time we do not know what the height is, so we can't figure out EG just yet. But we do know what the velocity is at spot 4. It's 6 meters per second. So I can therefore figure out what my kinetic is by using 1/2 mv squared. 1/2 of the mass of the cart, which is 50, times the velocity, which is 6 meters per second, and squaring that gives me an EK value of 900 joules. Since the total mechanical energy is 2,000, that means the EG must be 1,100 joules. Now notice, we predicted wrong. If you look at the bar chart, we actually predicted the EK would be higher. But that was not true. And so we need to tweak our bar chart to make sure that we're being accurate here. I'm going to go ahead and make the EG a little bit higher, giving it 4 squares. And I'm going to make the EG a little bit higher. And I'm going to make the EK a little bit lower, giving it 3 squares. Because I still want to make it equal to make sure that I show that energy is conserved. All right, we're going to do one last thing in this video. The last thing I want to do, now that we know all of our energies, is I'd like to solve some values. I would like to know 3 things. 1, what is the velocity at spot 2? 2, what is the velocity at spot 3? And then 3, what is the height at spot 4? Velocities are going to come from your kinetic energy, and height is going to come from your potential energy. At spot 2, you'll remember that we calculated the kinetic energy to be 500 joules. Since the kinetic energy is 500 joules, we're going to use our kinetic energy formula of 1/2 mv squared, and we're going to plug in the values that we have. The kinetic energy is 500 joules. That's equal to 1/2 the mass, which is 50, and then my velocity squared. If I go ahead and isolate v squared by taking 500 divided by 0.5 and then divided by 50, I end up getting 20 equals v squared. Don't forget to square root both sides, and I end up getting for my velocity as approximately 4.47 meters per second. This is the velocity at spot 2, or when the cart is at the top of the loop. Let's go ahead and do the same thing now, but for spot 3. At spot 3, my kinetic energy is 2,000 joules, so I'm going to set this equal to 1/2 50 v squared. If I isolate what v squared is by taking 2,000 divided by 1/2 and divided by 50, that's going to give me 80. Taking the square root of both sides is going to give me my answer of approximately 8.9 meters per second. And then finally, at spot 4, the height is going to come from our gravitational energy, which is 1,100. Gravitational energy is equal to mass times g times height. So 1,100 joules is equal to the mass, which is 50, times 10 to solve for our h. If I solve for h, I will end up getting h equals about 2.2 meters. This concludes the video on the roller coaster example.